Hi, my name is Scott Simpson, and today we'll be talking about intermolecular attraction forces. So intermolecular attraction forces are forces that occur between two adjacent molecules. So if you have an ensemble or a collection of molecules next to one another, they'll interact with one another to try and lower the total energy of the system. So what these are forces between molecules. So let's look at an example of this. We're going to ask, how does a dimer of water interact with one another? Or what I mean by a dimer is two of the molecules interacting with one another. So how does a dimer of water interact? Okay, so first we have to consider the structure of water. We can draw the Lewis structure pretty quickly. Everybody knows that. Now let's consider differences in electronegativity. We know that there will be some difference in electronegativity based upon having two different elements attached to one another. So we have oxygen, which is highly electronegative, attached to a hydrogen. So we know that this oxygen is going to become partially negative. And we know these hydrogens become partially positive. So now if we think about how two water molecules will interact, basically the negative end will want to meet up with a positive end because like charges attract one another. We know this from physics, of the adjacent water molecule. So if we have two water molecules near one another, they should want to interact with one another in some sort of fashion, where we have a partial negative with these oxygens, negative, and a partial positive with these hydrogens. And then we know, based upon Coulombic interactions, like charges attract, or like charges repel one another, opposite charges attract. We should get an attraction between that oxygen and that hydrogen. And this attraction here, this is the intermolecular attraction forces. Now, there are four different types of forces. There's considered to be four different types of forces between molecules. So forces are, we have dipole-dipole interactions. And these are interactions between polar compounds. So interaction between polar compounds. And this is where the dipoles interact with one another. So they try to cancel out an overall charge, essentially. They're trying to have the system of the energy of the system be as low as possible. So as an example, let's consider HCl. So we have hydrogen and chlorine attached to one another. We'll assume this is in a gaseous state, so it isn't under aqueous conditions where this would be a strong acid and split apart. We get a partial positive on this side and a partial negative on the chlorine side because the chlorine's more electronegative than the hydrogen. If we draw out the dipole moment of the molecule, it looks something like that. Now, let's say we have two of these molecules interacting with one another. There are two possibilities, well, a handful of possibilities of different ways that these molecules could interact with one another. We could have the chlorines pointed towards one another. We could have the chlorine pointing at a hydrogen, and then we could have another set where instead of having them interact end to end like this, we could have them interact side to side, like so. HCl, HCl. Okay, how would these systems want to interact? Well, let's draw out the dipole moments of each of these systems. Keeping in mind the arrows point towards the more electronegative system. or more electronegative element. Then we have like that, that way, and that way. Okay. So looking at these, we can see, we know that there's going to be a negative interaction here. This will actually be a repulsion. Because remember, we have partial negative here. These don't like one another. Now, in this case, there should actually be a slight attraction between the two. Attraction. Now let's consider if they're stacked kind of side to side like this. This hydrogen will be interacting with the chlorine. Let's get out purple so we can see a little bit different. This hydrogen will be interacting with the chlorine, and that hydrogen will be interacting with that chlorine. So this system will actually be an attraction. Now, if we consider the other side, this hydrogen's interacting with that hydrogen, that chlorine's interacting with that chlorine. These have partial negative, these guys have partial positive, so this will be a repulsion. So most of the time, you'll find the molecules in one of these two orientations, because those are the end most low in energy. It's more energetically favorable. And this interaction that lowers that energy, again, it's known as a dipole-dipole interaction. Okay, so that's the first force. We have dipole-dipole interactions. The second force we're going to talk about, which we've already discussed in class a couple times, is ion-dipole interactions. And what this is it is a polar molecule interacting with an anion or a cation. Interacting with an anion or a cation. We can see an example of this. Let's say we look at a sodium cation in water. So we have our sodium cation, which has a positive charge. Now we have to think about how will the water molecules surround this thing. Thinking back to our structure of water again, we said that these hydrogens will have a partial positive and a partial negative end. So since there's a formal positive 1 charge on the sodium, we have to consider how these water molecules will interact. And again, remember, opposite charges attract. So in this case, the oxygen will be pointing towards that sodium. And these waters coordinating around this cation, this is known as a sphere of hydration, but this is actually the attraction here. So it's a stabilizing interaction. So these negative ends, they all point towards that positive end. And that's an energy lowering interaction. So those are ion-dipole interactions. Now, the third type of bond, or excuse me, a third type of intermolecular attraction force are known as hydrogen bonds. And these are a specific type of dipole-dipole interactions, so specific dipole-dipole interaction. That has to involve nitrogen, oxygen, or fluorine. Involving nitrogen, oxygen, or fluorine. And what it is, it's kind of a combination of a dipole-dipole interaction and an ion-dipole interaction. So halfway between an ion-dipole and dipole-dipole interaction. So let's look at an example. Let's consider our friend water again. Water has a ton of hydrogen bonds. This actually explains why water is less dense when it freezes compared to the liquid state. So if we plunk one water molecule, we already drew a low energy structure earlier. It looks something like this. So in this case, the lone pair on this oxygen is attracted to this hydrogen. And what happens is there's sort of like a quasi bond that forms here, and this bond will get weaker. This happens throughout the system though. So that's why it's considered to be between an ionic and a dipole interaction and a dipole-dipole interaction. The fourth type of intermolecular attraction force is by far the weakest, but it's the most difficult to explain. It's known as dispersion. Some people call this London dispersion or van der Waals forces. What this is they're dipoles that form from the instantaneous fluctuation of electron density. So electron density starts to get perturbed, it gets moved around, and when that happens, you create partial positives and partial negatives. They're really weak, but still, this influences the overall interaction between molecules. So it's the formation, the force that results from the formation of instantaneous dipoles. Dipoles. And these dipoles come about due to the fluctuation in electron density. The other important point is all systems with electron density experience this. So pretty much all the systems we talk about in chemistry, they all have dispersion forces. Experience this. Okay, so let's try and explain this with pictures. So let's consider we have two helium atoms. So we have two helium atoms, and let's say we push one of these helium atoms towards the other. So we're going to move the right one closer to the left one. What I'm going to do is I'm going to draw the nucleus as little dot points. And I'm going to exaggerate what happens to the electron density. So as we push this one closer, what happens is these negative charges see one another, and it pushes the electron density out from this system. So if you look where that nucleus is, the electron density has been pushed away by this guy. And what happens is you get a bunch of partial negatives along this side because there's an accumulation of charge. And then there's a partial positive along this side because there's a lack of charge where it should be. Then when this starts to happen, the same thing happens to this guy. It keeps on being attracted more. So you have this negative charge here that's attracted to that partial positive that starts to form. And because the electron density is kind of getting squished over this way, you form a partial positive on this side. And then this creates, again, an attraction force between the two. So we squish electron density, it becomes polarized. And what we mean by that is you can move it pretty easily from the center or from the nucleus. And we create these instantaneous dipoles and they attract one another. Okay, so those are the four different forces. We didn't put a 4 for that dispersion, so we'll do that. Let's talk about their strengths. So by far the strongest is considered to be ion-dipole. It's considered to be the strongest intermolecular attraction force. Then, depending on what chemist you talk to, some would consider hydrogen bonds to be the next strongest. and then dipole-dipole. Now, these two can be really close to one another in energy. It really depends on the system you're considering. So for example, HF is really strong hydrogen bonds, but then as you start to change that system up quite a bit, you actually change the strength, so the dipole-dipole interaction might be stronger. But what we can all agree upon is by far the weakest is dispersion forces. They're incredibly weak. So how do we determine what type of intermolecular attraction forces our system has? So the first thing we have to do is we have to consider if we have an ionic or we have a covalent substance, or if we have a mixture of the two. Now with covalent compounds, we know we can have polar compounds, so these are ones with a molecular dipole, or we can have non-polar compounds, which have no net dipole. Non-polar compounds, they only have dispersion forces. There's no other forces that occur in these systems. Of course, polar systems do also have dispersion. Now, if you have a polar compound, it's going to experience a dipole-dipole interaction. Because you have the formation of a dipole, they're going to try and line with one another to lower the energy. Now, some polar covalent compounds can have hydrogen bonds or H bonds, but remember, if you think back to what I said about them, they must have a nitrogen, oxygen, or fluorine. Okay, so what about ionic species? If you have an ionic compound interacting with a polar compound, what you're going to get is an ion-dipole interaction. And of course, this species still has dispersion. If you're considering that you have a large number of polar solvent molecules, you're going to have dipole-dipole interactions. And if it's water or something similar to that, you may have H bonds. So we're going to put dashes along here. Okay, so now let's use this thought map to determine, example, what's intermolecular attraction forces do, we'll say A, methane, B, hydrogen sulfide. What do these have? So first thing is we have to decide, are these compounds ionic or covalent? Looking at the atoms that are involved, it's clear to see that these guys are covalent compounds. They have slight differences in electronegativity between the elements that make them up. So these are both covalent. Next, we have to determine if they are polar or non-polar, and we do that by drawing the Lewis structures and then considering the bond dipoles. So I'm going to draw a three-dimensional representation of methane, and then we have hydrogen sulfide. Okay, if we draw out all the bond dipoles for methane, what we notice is they're all equal and they're all pointing in the same direction. Therefore, there is no net dipole, and this compound is nonpolar. And since it's nonpolar, the only intermolecular attraction force it has is dispersion. Let's consider H2S. If we draw out the bond dipoles for this system, remember sulfur is more electronegative than hydrogen. There is a net dipole and it's pointing in this direction. So the net dipole is not equal to 0. That means the compound is polar. Okay, so now we're at this point, we have a polar system. We know we definitely have dispersion because every system has dispersion. So let's write that down. Okay. Now, since it's polar, we have to have a dipole-dipole interaction. So let's write dipole-dipole. Okay, would we have an ion-dipole interaction? The answer to that is no, because we do not have an ionic compound interacting with our polar compound, so that's out. Last thing we have to consider, well, the system is hydrogens. Does it have hydrogen bonds? If we look, okay, it only has hydrogen bonds if we have nitrogen, oxygen, or fluorine. Since we do not have any of those elements interacting with the hydrogen, these are the only two intermolecular attraction forces that we have. So H2S only have dispersion and dipole-dipole interactions. Okay, with that, I'm going to leave you. Hopefully I have taught you how to, one, assess what intermolecular attraction forces a system will have and what these intermolecular attraction forces are. If you have any questions or comments, please feel free to leave them below or contact me via email. Thank you.